team. Look, I'll do when you're on the second one.
All right, number one, it's asking us to evaluate the function. So you could do it one of two ways. Juliana, we're working on the packet now. So you do it one of two ways. You could plug the -2 in for x and simplify, or you could do it the easier way, which would be to plug it into your calculator and just hit enter. All right. So the way you would plug it into the calculator, it could be a couple of different approaches, but in this case, it's just one function that you're working with. So 4 times -2 to the third power minus 17 times -2 plus 2, call it a day. All right. So in the second case, we're evaluating it for x equals -1/3. So you do the same thing. So g of 1/3, or same approach anyway. So actually, just to get the notation right on this one, I should write also f of -2 is equal to 4. So you're popping in the 1/3 here. So -9 times 1/3 to the second power plus 3 times 1/3. Now this one is easy enough that you probably could have done by hand, but you don't need to. That's the whole point. All right, so if you're thinking back to the activity from Friday, maybe you're thinking back to that activity with a little bit of regret, because on the blue station, the first two problems were basically that. You just pop it in your calculator. There's no reason to do any of that by hand. All right. So the two things that these functions have in common, or one thing that they have in common actually, is that they're both what we call polynomials. All right. So this whole unit is based off of polynomials, and polynomials are they have a lot of characteristics associated with them, but polynomials by definition really are the product of linear functions. All right, so we'll get to that in a few minutes, but we started off learning, we spent a lot of time in the course learning about linear equations and inequalities and functions. Now what we're going to do is we're going to expand it by operating with those linear equations by multiplying. All right, so when you multiply linear equations, you get polynomials. All right, and so, okay, that's annoying. So we're gonna spend a lot of time exploring what those characteristics are. All right, so I'm gonna turn my calculator off. So a term is an expression that is separated from another expression with either a plus or minus. All right, so if I go back to the first example, we have f of x equals 4x cubed minus 17x plus 2. Again, it's an expression that's separated from another expression with either a plus or minus. All right, what we're looking at here are 3 separate terms. All right. All right, so 3 terms to the, well, we're going to use the word expression a lot because you have 3 individual expressions that make up one bigger expression. All right, but those smaller expressions we call terms. All right, so the coefficient is a constant multiplier, also known as a scalar multiplier. of a term. So, for example, we have 4x cubed as a term. The coefficient of that, the constant multiplier, would just be the 4. Anybody know what a constant is? So that would be a coefficient, another way of expressing a coefficient. So that's a good alternate definition of coefficient. So it's still a good contribution. Yeah, number that goes in front of a variable could be another way of describing what a coefficient is. So very good. All right. A constant is separate from that. It does not. Well, constant values do not vary. So what does that tell you about a value that would be constant? What would it not have?
It wouldn't have a variable.
It would not have a variable. All right. So a term that does not contain a variable all right. So a term that does not contain a variable. Now, in most cases, that usually means some kind of number, like 2. 2 is a constant, 2 doesn't change. All right. So I'll give you that as an example. But it could also be something like pi, the square root of 7. All right, none of these contain variables. All right, maybe an exponential, maybe something like 3 to the 5th power. Still no variable. All right, we're not going to do much with what we call transcendental functions this year, which is exponential, logarithmic, and trigonometric functions. But I'm going to write one anyway, a trig function. So something like the sine of 2. All right. So sine is another type of function. It's a trig function, and you'll explore that a lot. You know, you're going to see that. And you actually might see it in science class before you see it in math class, right? So, but bottom line is it's another type of function. You could see the key on your calculator, right? It says sin, right? But it doesn't. My point is you have another function here that does not contain a variable, all right? So there's no x there. So all of these would be considered constant, all right? Monomials. Single-termed expression. Example, something like 4x cubed. All right, there's nothing being added to it or subtracted from it. What do you think polynomial, the definition would be? Multiple termed expression. Where else have you heard the term mono and poly? Like in what other class, everyday life?
In global.
In global? What was the term? Or what were the terms?
Polytheism.
Yeah, polytheism, polytheistic, and monotheistic. Right? So it's the same idea. You know, individual, single, versus multi. Yeah. So an example here, just really anything that has more than one term is going to be considered a polynomial. Right, the one I had at the top there, that would be a polynomial. But even something like 2x minus 3, You could, I'll even put the 4x cubed one. Plus 2 is what it said. All right, degree's a weird one because there's like, trying to think from stat class, because we talked about degree for in a different context, but we came up with about 6 or 7 different definitions of the term degree. All right, but the ones that you typically think of won't necessarily apply in this situation. I mean, generally, most people, prior to experiencing a lesson on this, were not thinking that degree meant the highest power in a polynomial. All right, so for example, 4x cubed minus 17x plus 2, the highest power out of all the powers available, oh, that is not a highlighter, would be 3. What's my lowest power here?
1.
You would think it would be 1, but it's not, because after the 2, there's an understood x to the 0th. So the highest power is 3. The lowest power is actually going to be a 0, right? So it's kind of strange to think about it that way, but when you're thinking in terms of polynomials, you have to think even the standalone constant could have a multiplier with an unchanging variable. When you think about a variable that doesn't change, it's kind of weird. Leading coefficient. It's the, well, not to insult your intelligence, but it's the coefficient that leads the expression, right? But there's something that has to be in place in order for that to happen, right? So the with the polynomial in descending order, bless you. Like the ordinary width, not like width. Kind of wrote it in Yoda speak here, backwards. The idea being that it's so important that the polynomial is in descending order that you got to account for that first, right? So, because what'll happen is, and I'll show you a couple of examples here. One, the one that we're used to, 4x cubed minus 17x plus 2. And then another one, let's say 2 minus 4x to the 5th, assuming it wants to write, minus 7x. All right, so the first one's already in descending order, and all descending order means is it's arranged based off of its exponents. So the higher exponents come first, right? And then they're ordered based off of that, right? So I have a power of 3 first, then a power of 1, then a power of 0, right? In the second example, so in the first example, the leading coefficient would be 4, right? In the second example, the leading coefficient, I mean, if you just think, okay, well, leading coefficient that leads, 2, well, that wouldn't be correct. That's not going to be correct because it's not in descending order. The proper order for the second example would be negative 4x to the 5th minus 7x plus 2. All right, so all you have to do really is identify the term that has the highest exponent. Whatever the coefficient is of that term, that's going to be the leading coefficient. All right, so in this case, it's a negative 4. All right, but you could have picked that out without rearranging the whole thing. All right, so it's pretty, well, I was going to say it's pretty important. It's incredibly important because a lot of the things that we do with polynomials is based off of the knowledge of what the different coefficients are. All right, so we have actual formulas that we use to solve equations for polynomials that will not work unless you're able to identify what the leading coefficient is. Also, we can make determinations of what the graphs look like of a polynomial based off of the leading coefficient itself. All right, so the standard form of a polynomial, f of x. So I wasn't kidding about that. That f of x stuff, it's never ever going away. It's always going to be there. All right, so we got to get comfortable with that. All right, so a times x minus h to the nth power plus k. All right. Every polynomial could be expressed in that form, and in fact, every function could be expressed in that form. So when we start expanding it to other types of functions, we could write it in that form also. Right? The reason why that's important is because depending on the type of function we're looking at, the h and k values usually represent the turning point, but it also could represent something called an inflection point. All right, so I'll show you really quickly what those look like. All right, so h comma k is either a turning point or inflection point. All right, the first term, turning point, I mean, I don't think that requires a definition. It's the point where it turns. So it didn't require it, but I gave it anyway. All right, so a graph is going to turn around, the point where it turns around. All right, if you're thinking about a parabola, you know, the U-shaped curve, it would be the lowest point if it's an upward-facing parabola, or it would be the highest point if it's a downward-facing parabola. Right? That's very important information because that helps us determine extrema, right? Maximum and minimum values. Right? But the inflection point, that's weird. Right? So I'll draw a couple of quick diagrams here. One is just your ordinary parabola, and the other is a cubic function. So this is a parabola. And this is cubic. All right. Sometimes people purposely pronounce parabola incorrectly so that they remember how to spell it. So I'll hear people say parabola a lot, but I mean, it's not what it is, but it helps them remember how to spell it, so that's fine. I don't think I've ever taken off credit on a test or a quiz for somebody misspelling parabola. I have laughed at some of the spellings, but I've never taken off credit. The only time I ever get like peeved is when the question, it actually uses the word in the phrasing of the question. It'll say like, what is the turning point of the parabola? And then in your conclusion, you write the turning point of the palabra is this. And it's like, it said it right there. So how did you screw that up? You know, but so this is our turning point, the TP. And then this right here is what we call a point of inflection. And I'll explain how we know that in a sec. All right, abbreviation POI. These are my abbreviations, so That abbreviation rules apply, which just basically means the same thing as it always meant. You could use the abbreviations on my tests or quizzes, but on the Regents, just write the whole word, the terms out. All right, especially point of inflection, because you don't want to have to write that out a bunch of times. All right. So anyway, a point of inflection is what we call, it's based off of a change in concavity. All right. So you have two types of concavity. You have concave down and concave up. All right. So this part of the graph here is the part that's concave down. And this part of the graph is concave up. All right. The way that we know the concavity of the graph is just basically how it's bowed. All right. So it's going to be, because curves can be bowed in certain ways. All right. So if you take a graph and you bow it in a certain way, it's going to create a type of concavity. It's either going to be concave up or it's going to be concave down. All right. The concave up one should kind of start to look sort of like a U. U for up. All right, so that's what's happening here. So it's not a full U, but it's enough of a U that it kind of leads. It's definitely not going downward. If you were to try to match, and this is what a lot of people do, is they take a bendy ruler or they take a piece of paper or index card and they try to match it up with the graph and see what kind of shape it's creating. All right, if I try to match it up with this portion of the graph, it's going to be bowed in a downward direction. Right, it becomes a little bit more obvious. The classic textbook definitions for concave down and up, it's really kind of strange, but this is actually written in calculus textbooks. They say concave up is a graph that would hold water, and concave down is one that would spill water. And I'm like, that's really mathy. So, but I guess, yeah. I mean, I don't know that this would hold much water, but this is more likely to hold water than this shape would. So I guess, you know, this, I don't know if it would spill the water, but it wouldn't collect the water. All right. But the abbreviation for concave up, I think it does a lot for helping us to understand what the definition is. Because the abbreviation for concave up is C up, like cup, all right? So if you want to go with that holds water definition, this actually kind of works, all right? But I think the bending paper, bendy ruler kind of approach is probably the better way to go. This isn't the best ruler for that, but you could see here, it's more like a U than this one is, all right? Where there's a change in concavity, that's where you have a point of inflection. All right, so why am I talking about all of this? Well, I got to kill a period. Now, it has to do with this. The H and K values will tell us those important characteristics of these graphs. All right, the one thing that those 2 points, whether it's a point of inflection or an extreme value, the one thing that they have in common is that they're the central point in the graph. All right, so if you want to know where a graph is centered, it's going to be at one of these 2 points, the H and K values. All right, so H and K gives a coordinate that is designated as the center of the graph. All right, so now I know where to focus my attention when I'm going into the graphing calculator, because you're going to see some functions, some polynomial functions, where you're going to hit graph on your calculator and nothing's going to show up. And you'll be like, well, I typed it incorrectly. You'll go to the table though, and you'll see some values in like the 10,000s. And you'll be like, well, how am I supposed to come up with a window for that? All right? The H and K values are that's what's going to help you come up with a window. All right? So this is a lot of just background information, because what I've discovered in the past is that this stuff here, like terms, not like terms, and things, that's all stuff that you could read through and understand pretty easily. And then the stuff on the next page, right? But what tends to be the case is that students, they go through this entire unit and they get really good at adding terms, multiplying terms, and all that good stuff, popping stuff in the calculator, but they never really understand why they're doing it, right? So I'm going to keep coming back to these terms repeatedly throughout the course, and it's going to become part of the vocabulary. In fact, this stuff is going to end up on the wall. All right. So that's how important this stuff is, right? Because like a term like degree, when I say degree, I don't want you necessarily thinking about temperature, unless snow's on the horizon. I don't know. I haven't been checking the forecast, but there was one year where we had a snow day the day before Thanksgiving.
That'd be great.
That was the happiest day of my life.
We also get 2 weeks off Christmas.
Which is sad because I have a wedding in there, I have the birth of my son in there. College graduation, like all of these different things. But really, it was the day that I woke up, the day before Thanksgiving, and I was surprised with the fact that I did not have to go to school that day. That I openly started weeping, tears of joy. So that's what I'm. That's a little bit about me and snow days if you didn't already know. It's one of those like you wouldn't necessarily know this, but and I'm not really like kind of tooting my own horn here, but like when there's weather on the horizon, I'm the person everybody comes to ask, yo, what's the deal? Are we gonna be out tomorrow? Because I've never been wrong. We're not going to be out tomorrow. All right, but one thing I can promise you is that we're not going to do anything in the packet tomorrow. All right, tomorrow's going to be a fun day. All right.
Candy day.
But that
It's gonna be candy day.
I'm not a candy guy, but you're welcome to bring candy. I don't eat candy. It's not my thing. It's not my vice.